SI tonight, so go if you can. We started yesterday talking about benzene and aromaticity. And we went through the process of how to decide when we look at a molecule whether it's actually aromatic or not. Okay, so hopefully we're good on that. And today what we're going to do is we are going to talk a little bit about how aromaticity can affect some reactions. We'll look at a couple of acid-base reactions as our first examples. We'll talk a little bit about how we might get a handle on just how much stabilization we get from making a molecule aromatic, and then we'll learn how to name aromatic benzene, substituted benzene compounds. All right? Yeah, question? Did
you figure out if the benzoate pyrene had a...
Oh yeah, so that was a good question. So I had a question yesterday. Remember I put up, if I can remember how to draw this structure, I think it was a whole bunch of these things. Maybe one more over here. Is that right? Let's see if we can just draw these alternating bonds all the way around the out. No, something's wrong there. Oh, there's the problem. Something like that. All right, so the question was, and then there must be something still not right there. Let me try again. So there's different resonance forms that we can draw for these, but we want to make sure that there's a double bond going to every carbon. Let's start here. Goes to there. I'll just put one here and here, and here and here, and here, and here and here. No, that's not right either. Can't even do it. Oh, good. I got to copy my own stuff. I can figure it out on my own.
Oh, okay.
If I could just draw right. Okay, there's that one. Let's go ahead and put this one. No, there must be something wrong with this. If I can't do it, then it's not aromatic. How about that? All right, so the question was, I said that this compound was aromatic. It's produced, so it's called oops, can't spell either. Was it pyrene? Pyrene. It's produced in tobacco, cigarette smoke. And it looks aromatic. It just has a bunch of benzene-like rings. But when we actually add up the number of electrons, it comes up to 20 pi electrons, and that should be anti-aromatic if we follow this Huckel's rule. So I did look it up today, and I didn't really draw the best resonance form for this, but essentially what they said, well, there were two explanations. One is if you get too many rings like this, it doesn't really matter what the count is. It just ends up being aromatic. The other one was that you essentially look around the outside of the ring, so around the periphery, and you kind of ignore these two that are in the middle. And so if I drew a different resonance form where it had an actual double bond at that place, you just kind of ignore one of the double bonds that's in the middle of the ring, and you're looking at the pi system that goes around the whole periphery. So that removes two hydrogens, and so you end up getting 18 pi electrons. But you have to have, we got to have a better, I don't want to take all day doing this. If I could only... It's that song, If I Only Had a Brain. Let's see. Let's start the other way. Just go around the outside first. Like this, and then there'd be one in the middle. I think this is the way it is. And so notice that if you go around the outside, there's a double bond to every carbon around the outside. There's a p orbital on every one. But this double bond is kind of isolated in the middle. And you can have the pi system go all the way around here without involving that middle double bond. Okay, so the middle one is not really involved. So the ways that they can tell that, well, they can tell that it's planar. The other thing, remember when we talked about NMR, that there was this ring current thing, which is why the protons on benzene were so far downfield. And they see the same thing here. And so that tells us that it is aromatic and there are ring currents. Okay? Seems like there was another question I was going to look up too, but I forgot. Okay, so like I was saying, this is what we're going to do today. Don't you think? All right, so what we're going to do now is we are going to look at how aromaticity can affect some reactions. In the next chapter, we'll actually look at reactions of benzene. Oh, this is where I should have had this. Okay, so let's look at these two molecules, okay? And we're going to consider them for their acidity. Would you think right off the bat, if you look at those compounds or those compound types, that you would think would be acidic? No, not really, right? It looks like they have hydrogens either on sp2 or sp3 hybridized carbons, and that's usually not a very acidic situation. Okay, but it turns out, and I didn't bring my notes because I thought I remembered it all, but I didn't really remember these. Huh?
Can you turn it on for us? Can you switch the computer to your iPad?
Oh.
There you go.
There's that better. All right, now, do you think that those look like acids? Not really, huh? Turns out, though, that this bottom one has a pKa of 15. All right, so what, as far as acids go, what does that put it in the same range as? Water, right? Water has a pKa of 15.7, so this molecule is actually more acidic than water. Means that its conjugate base must be even more stable than hydroxide, I guess, right? I don't remember off the top of my head what the pKa of this top one is, but it's much higher, okay? They look almost the same. This has a pKa that is much higher. So for some reason, even though these kind of look the same, the conjugate base for this one must be much less stable. Okay, so let's draw out the conjugate bases, see if we can figure out why one has a very stable conjugate base, one doesn't. Okay, so let's take off. We're going to take off one of those protons that look like they're on a sp. Well, here's the acid. The proton plus this. It's going to leave a pair of electrons behind, so it's going to have a minus charge. Okay, so this is the conjugate base for this cycloheptatriene. If we do it for the bottom one, we have the same kind of deal. This is the conjugate base for that cyclopentadiene. Okay? So, for some reason, the bottom one is more stable than the top one. All right, so why is that? Yeah, up here.
Because there's an odd number of pi electrons.
Yeah, so what does it make the molecule? It's aromatic. All right, this one down here is aromatic because it has 2, 4, 6 pi electrons. Okay, if we draw it from the side, we could draw it like this, right? So now, if that position hybridizes as sp2, then we get a system that looks like this. 2 electrons here, plus 1 from each of the other carbons. And so we have 6 pi electrons. All right? So this system is what we could call being isoelectronic to several of the systems we looked at yesterday. Right? This kind of system is the same as what we saw for this. Right? Because we had one non-bonding pair that went into a p orbital to make it aromatic. It's isoelectronic to this one. Right? Because again, in fact, this pyrrole looks a lot like this cyclopentadienyl anion, right? In that it has exactly the same situation. It even has the hydrogen there. It's just that with the carbon it has a minus charge because carbon has, one fewer valence electron, so when it has that extra electron, it has a minus charge. So all of these, we also looked at this one with an oxygen here, right? All of these have the same electronic structure, okay? In each case, there's one of those atoms that's adding 2 electrons to the system rather than 1. That allows it to have 6 pi electrons, makes it aromatic. What about this upper one? Does it have the correct number of electrons to be aromatic? No, because it has 2, 4, 6, 8. It has 8 pi electrons. Right? So if it's planar, right, it would be anti-aromatic. Okay? I'm not so sure it stays planar, but if it was planar, it would be anti-aromatic, whereas this one down here is aromatic. Okay? What do you think with this 7-membered ring up there? Is there another ionization state where we could make a 7-membered ring like that be aromatic? How many electrons would we want to have? Well, we started out with 6 in there already. What would make it aromatic? In fact, if we have a cation here, all right, then because a carbocation is sp2 hybridized, it has an empty p orbital, now we have 6 pi electrons spread around 7 atoms, and it's aromatic. Okay. What do you think about the cyclopentadienyl cation. Would that be aromatic? No, because it has 4 pi electrons. That's the wrong number, right? So this would not be aromatic, and it wouldn't form very easily, right? This one has a much higher pKa because it doesn't want to give up a proton. It doesn't want to form this species that would be anti-aromatic. Okay? Here, what about this one? That would be aromatic. All right? Doesn't seem like it'd be super stable, 3-membered ring, but it has 2 pi electrons. It has a p orbital on every carbon. So this is also aromatic. All right, so we can have different ions. By changing the ionization state, it can change the number of pi electrons that are put into the pi system, right? And change whether it's aromatic or not. One more acid-base reaction. Okay, this molecule is called imidazole, and it is a common organic base. It also is part of an amino acid. It's on the end of a chain in an amino acid in the amino acid histidine. Okay, so imidazole has 2 nitrogens. Each nitrogen has a non-bonding pair of electrons on it. Right? So either of these nitrogens could act as a base. Right? It has a pair of electrons it can donate to react with a proton. So the question is, which of those 2 nitrogens, so nitrogen A or nitrogen B, is more basic? Okay? So let's just draw out. So we're starting now with a base. Let's draw out what the conjugate acid would look like. Okay, so if we go up this way, if we react nitrogen A with a proton, we will get a conjugate acid. That looks like this, with 2 H's on this nitrogen. Okay? Alternatively, if we add an H plus to nitrogen B, we get another possible conjugate acid. This one has an H already. We've added an H here. Now this bottom nitrogen has 4 bonds to it, right? So it has a plus charge. So what do you think? So in this case, we started with the same acid. We're forming 2 different conjugate bases. So it's kind of the reverse of our normal acid looking at different conjugate bases, right? So whichever of these conjugate acids is more stable would be the one that would more readily form. All right, so which of those 2 conjugate acids are more stable? The top one or the bottom one? How many people think the top one? Raise your hand. Okay. Why do you think the top one?
Because the plus charge that connects the circle.
Mm-hmm. It does. Okay. How many people think it's the bottom one? Okay. A few more. Why does somebody think it's the bottom one?
Because it's aromatic.
Yeah, it's because the bottom one is aromatic. The top one, is the top one aromatic? No. Why not? Right, because this nitrogen now has a complete octet of electrons. It has to be sp3 hybridized. it has 4 sigma bonds. Okay, and when we have a pi system that's interrupted by an sp3 hybridized atom, it cannot be aromatic. Okay, so that means that this nitrogen B is going to be the preferred conjugate acid. All right, so it's not going to go this way, it's going to go down to the bottom. So what does that mean? Which nitrogen, A or B, is more basic? B, right? Because the more basic nitrogen is going to be the one that more readily reacts with a proton. Okay, so nitrogen B is more basic. Okay, because its conjugate acid is more stable. All right, does that make sense? All right. What's the big deal? Oh, no, I have one more example here. So in DNA, it has these different DNA bases. Okay? And so, you know, they're based upon kind of a basic unit. There's this molecule called pyrimidine, which only doesn't have these oxygens and stuff. It just has the main ring with 2 nitrogens in it. Okay, and then we can make it look like a normal aromatic ring. This other one is based on the structure of purine. It has 2 rings. All right, but notice that in all but adenine still has nicely alternating double bonds, right? And then in the 5-membered ring, notice it has this non-bonding pair, so that could be donated into the pi system to make both rings aromatic. But the other ones, look at it's not so clear, because like in guanine over here, look at the way it's usually drawn. It has a nitrogen with an H on it, right? There's no double bond in the ring there, right? But they still call this aromatic. Look at thymine has 2 carbonyls drawn like this, right? So generally, these are called aromatic, and it's because there is some considerable participation from a resonance structure. Okay, so we can draw a resonance structure from this amide, where these electrons go down and the electrons are spread up onto the oxygen. Okay, so this gives us a resonance structure that looks like this. Okay, this has the NH2 out here, double bond, O minus plus, like this. Like that. And so because of this resonance structure, now we can see that we kind of have, you know, pi electrons that can be all the way around the ring. Okay? We know that this one on the left is more stable because that's what's actually observed in DNA, and because if you remember, you know, from biology or something, these base pairs hydrogen bond with each other, and so thymine and adenine, give 2 different hydrogen bonds. Remember, a hydrogen bond is just really a dipolar interaction between an electronegative atom and a hydrogen that's attached to a more electronegative atom. So we have a delta plus on the hydrogen, delta minus on the oxygen in this case. Again here, delta plus on this hydrogen, delta minus on the nitrogen. The nitrogen has a pair of electrons. Okay, so thymine and adenine make 2 hydrogen bonds. Guanine and cytosine make 3. Okay, so we get these kind of hydrogen bonds, and those keeping this double helix shape of DNA. So this is from the book. It's a little hard to see, but they show hydrogen bonds between the different atoms, but there's also a different interaction here, and that's these aromatic base pairs kind of stack on top of one another, right? So right here, there's two bases that are getting pushed down on top of each other, so the p orbitals of each system kind of interact sideways. So those are stacking, these are stacking, and remember that's what I said is some of those polyaromatic compounds can slip right in between those, and that was a process called intercalation, and it causes some can cause DNA damage and things like that. All right, so aromatic compounds are important all over the place in bio. Okay, so what about this big energy savings that we've been talking about, right? We've been saying, oh, you know, aromatic compounds are so stable and, you know, that kind of thing. So how do we even know that, you know? So we could test this ourselves if we had an apparatus to do this. And what we do is, like you probably talked about when you were talking about stability of alkenes, is that we look at heats of hydrogenation. So we could take a molecule like cyclohexene, we react it with hydrogen and palladium on carbon, does electrophilic addition reaction, hydrogenates that to give us cyclohexane, gives off some energy, okay? If we have two alkenes, then we would kind of expect the amount of heat that's given off to be just twice as much, right? That makes sense, right? So if we do this cyclohexa 1,3-diene, then we get minus 232 kilojoules per mole. It's not exactly twice as much, but it's pretty close, all right? So if we go to benzene, or what we could call cyclohexa 1,3,5-triene, right? We'd expect that to give off about 3 times as much as we did up on the top, right? 3 times. So here's what might be calculated. 3 times 120 is minus 360, but in fact it only gives off 208 kilojoules per mole. So it's giving off way less than was expected. Okay? So how do we put this into perspective? A diagram here. Remember, the thing that's in common in all of these products, all these reactions, is the product. Okay? They're all giving cyclohexane as a product. So if we set the cyclohexane at 1 energy, the amount of energy that's given off in each of these reactions is how much higher in energy the starting material was, or the reactant was. So in this case, this is just showing the theoretical, kind of benzene. They kind of exaggerated this as what we would expect if there was no resonance. The single bonds would be longer than the double bonds. So we'd expect it to be up here, and when it hydrogenates, it should give off 360 kilojoules per mole. All right? But it only gives off 208. So we know that benzene is only 208 kilojoules per mole above cyclohexane. So it's this much lower in energy than what we expected. Okay? This energy, this stabilization, is called the resonance energy. And this is how much more stable benzene is than what we would expect without the resonance. All right? So it's 152 kilojoules per mole, and that's quite a bit, right? So in reactions, as we'll see in the next chapter, when benzene reacts, it's going to react in a way that helps it maintain its aromaticity, all right? It doesn't like to do reactions that breaks up the aromaticity in the ring, because that would be going at least 152 kilojoules per mole higher in energy. Okay? So that's going to really control the reactivity of benzene. Okay? And so we'll talk about that starting tomorrow. Is to learn how to name substituted benzenes. All right, so so these are all monosubstituted benzenes, right? And so for many monosubstituted benzenes, all we do is add a prefix for whatever the substituent is and then say benzene. Okay, so for example, upper left has a chlorine. We just call this chlorobenzene. All right? The next one over, do you know what this functional group is? A nitro group. This is just called nitrobenzene. Right? Here we've got ethyl group. This is ethylbenzene. Right? The next one obviously is called toluene. Right? The next one on the lower left, we got an OH on there. We don't call it hydroxybenzene, unfortunately. This is called phenol. All right. The next one isn't like aminobenzene, unfortunately. This is called aniline. Okay, so a lot of the monosubstituted benzenes and even some of the disubstituted benzene have common names that we use. All right? And I'm not going to ask you to remember all of these, but there are some of them. Here, I'll just write these out, though. This one is kind of benzene sulfonic acid. Okay, so that's a strong acid. It's kind of like sulfuric acid, right? It's just taken one OH off of sulfuric acid and put a benzene on there. This one is called anisole. Anisole, the name, just like when we talked about vanillin and cinnamic acid, comes from the plant, right? So you know what anise is, right? What does anise smell like? Like licorice, right? So anisole is the licorice smell. Okay, this is styrene, right? You've heard of polystyrene, so like the white plastic cups and stuff like that. That's a polymer of styrene. Okay, this next two are easy because there's what functional group is this? It's an aldehyde, right? So this is just called benzaldehyde. I like to say that one. Aldehyde, benzaldehyde. Okay, the next one's easy too. Benzoic acid. All right, and then this one is called benzonitrile. All right, so out of these, you should definitely know how to name these simple ones where we only add a prefix, right? And then I think we should know what toluene is, phenol, aniline, and then we should be able to remember benzaldehyde and benzoic acid. Okay, let's say that's good enough. Okay, so you should know those ones. It's just like learning some new words. All right, so on the bottom, if we have aromatic rings as substituents, so if they're attached to something, then we need to have some way to name it like an alkyl group or something like that. So the one on the left, where we just have a benzene that's attached to some parent, what do you think that should be called? it should be called phenyl. Seems like to me it is called phenyl. But it seems like it should be called like this one over here, right? Benzyl, right? Benzene on the left one seems like it'd be benzyl, right? But benzyl's with an extra CH2 group in there. Keep in mind, don't mix up phenyl with phenol, right? Phenol, OL, has the alcohol on it. All right, so of course you should know these two down here as well. All right, so it's just some different language. We're going to use these monosubstituted benzenes when we name, kind of disubstituted or polysubstituted benzenes. All right, so if we add two groups onto a benzene ring, we can have three different orientations. We looked at this in NMR when we were looking at the NMRs. We could have the two groups be on adjacent positions, so 1,2 disubstituted. We could have them 1,3 disubstituted or 1,4 disubstituted. When we name disubstituted compounds, we can either use the numbers 1, 2, 1, 3, 1, 4, or this language has been used where if it's 1, 2 disubstituted, it's called ortho. So ortho is a term that describes the relative position of two groups on a benzene ring. So they're on adjacent carbons. Sometimes you'll just see an O out in front. If they're 1,3, it's called meta. If it's 1,4, it's called para. Okay, so those tell the relative orientations of those two groups. I don't know what the history of these are. It could be that they came up with these things even before they practically knew what the structures looked like on some of these things. Some of those names, like anisole. It came from anise, and they isolated a compound that had that smell, so they called it anisole. Right? They didn't really know what the structure was. All right, so if we're going to name disubstituted, what we're going to do is we're going to first look at the structure and see if the structure contains any of those monosubstituted benzene compounds that we had to learn on the last slide. If it doesn't, then all we do is we list the substituents in alphabetical order. We either use this kind of terminology, ortho, meta, or para, or we put numbers. Okay, so this has a bromo and a chloro, so we could say meta, bromo, chloro, all in one word here, but I can't fit it, benzene. Okay? So we don't have to give it a 1 or a 3 or something. We just say they're ortho. We just list them in alphabetical order. We could give them numbers, and then we would give the bromo the number 1, right, because it comes first in the alphabet. So we could call this 1 bromo, 3 chloro benzene. Either one would be acceptable. All right, the next one, well, I'm not going to write it out. So we have an isopropyl and we have a nitro. All right, so it would be para isopropyl nitrobenzene. Okay, it just tells those two groups are 1,4 arrangement. Now the next one, notice that we have one of the monosubstituted benzenes that we learned in here. Right? So what's this one called? This is phenol. Okay, and so we can say that this is para isopropyl phenol. So it tells what the relative position of the isopropyl is compared to the functional group that's part of the name. Okay, or we could call it 4-isopropyl phenol. Okay, either one is fine. Okay, what about the bottom left? What's the parent? right here has the amine in it. This is called aniline. Okay, so this would be ortho ethyl aniline. Okay, or 2-ethyl aniline. All right, the middle one, you can do that on your own. This one on the right, this is benzoic acid, right, is the parent. So we could call this metachlorobenzoic acid, or 3-chlorobenzoic acid. Okay? Yeah, question?
What if you have two of the named groups?
Yeah, that's a good question. So if you have 2 of the named groups, then there has to be a priority system, but we're not even going to go there. All right? Sometimes when you have 2 of those priority groups, like if you have 2 methyl groups on a benzene ring, they're called xylene. So you could have ortho, meta, or paraxylene. Right? So there's a lot of those that are, if you have 2 OHs, they could be these resorcinols. If you have 2 OHs on a benzene, 2 phenols on a benzene ring, and a long chain, those are the kind of molecules that give you rashes from poison oak and poison ivy and stuff like that, or at least they do me. I don't know about you guys. All right, so and then we're going to move on into the next chapter and start talking about the reactivity of benzene. So the notes for that next chapter are all posted, so you can download those. All right, so I'll see you guys in the morning.